for the invitation, Human. So, hello everybody. So as Human said, I work in Gothenburg in Sweden at the University of Chalmers, and as well, I'm involved in an experiment there, but also I'm involved with experiments in Vienna. So I'll be moving to Vienna in Austria in 2 weeks' time to be working there. The experiments in Gothenburg and the experiments in Vienna are very closely related. In all of the experiments, we're trying to develop quantum systems which have got very large, very massive particles. So particles which weigh around about 1 microgram. And 1 microgram, that might not sound like very much, but it's very large for a quantum system. So 1 microgram is around about 10 to the power of 17 atomic mass units. So it's larger than most molecules that are out there. So with these experiments, we can go about asking some questions, or that's the motivation behind these experiments. We want to be able to see, are there limits to the sizes that quantum systems can be? And as well, we want to see if we can get any hints into whether or not we can unify quantum physics and general relativity. So let's look at the first one of these questions. Are there limits to the sizes of quantum systems? So we know that the macroscopic world of electrons and atoms and molecules and quarks and everything else, it's described extremely successfully by quantum physics and by quantum field theory. But our macroscopic world of apples and trains and buses and trees, it's not described by quantum physics at all. We don't see quantum phenomena there. And it isn't very clear why there's this divide. Another way of looking at this question is we can ask, why is there wave function collapse? This is called the measurement problem in quantum physics. So in quantum systems, there's in the very foundations of quantum physics, we've got 2 different types of dynamics that occur. We have smooth dynamics, which we call unitary evolution. And as well, we have an abrupt change of quantum systems that can occur whenever there's a measurement happen. And these 2 different types of dynamics seem to be at odds with each other. And to resolve this possible difference, so then to resolve these differences, some people have proposed that perhaps there is something fundamental in nature that causes quantum systems to just collapse, for the wave function, for the quantumness to be lost or the coherence to be lost, and the wave function to collapse onto to behave like a classical system. And that this collapse would happen faster in a larger system, in larger systems which have a heavier mass, and larger systems in which the superposition states are more spread out. And then that would be maybe the reason why we can see quantum effects in very small things like atoms, where the coherence lives for longer and this collapse is more slow. Whereas for bigger things, we don't see, we can't see quantum effects because the collapse would be much more quick. Okay, so there's a variety of collapse models out there, and none of them have been shown to be true yet, but it's something that we want to investigate. So one of the collapse models, for instance, is called the Diossi-Penrose model. And in this model, the collapse occurs because of gravity. So the reasoning goes as follows. We know from general relativity that masses distort space-time. And so then if we have a mass prepared in a quantum superposition of 2 different locations, then space-time will be distorted in 2 different ways, all at the same time. So here we've got this red ball in 2 different positions, and there's 2 different corresponding spacetimes. But then the reasoning goes that space-time doesn't like to be in a superposition of states. And because this might lead to some problems with causality. And so then space-time causes the wave function to collapse. And and then this collapse would happen at a higher rate if there's a larger masses involved, or if there's larger sizes of the superposition states, because then the differences between the space-time superpositions would be larger. And so that's the approach that was proposed by DOC and Penrose. But as well, there's a bunch of other collapse models that are out there, and most of them don't relate to gravity, actually. But the DOC Penrose model is quite popular. Though none of the collapse models have been shown to be true. And the great thing about them is that they're testable. So we could go about probing these collapse models by preparing a quantum system with a large mass or a large spatial extent, and looking at, will the quantumness get lost? Will there be a spontaneous collapse of the wave function? So one could go about doing this with a double slit experiment, for instance. So here we've got a large molecule, a buckyball, which goes through the two slits, and then the two different paths interfere with each other when they get to the detector, and we see this interference pattern here. So this interference pattern shows that there was coherence maintained in the system from the slits to the detector, so there wasn't any collapse occurring for this buckyball. And experimentalists are trying to prepare larger and larger, carry out similar experiments with larger and larger particles, larger and larger molecules, to test these collapse models in regimes with larger masses. But it's not just these kind of matter wave interferometry experiments that can be used. As well, we could go about using systems with trapped particles. So then in these systems, we could prepare, instead of preparing the particle in a superposition of locations, we could prepare the particle in a superposition of motional states, and then look at how long the coherence would be preserved in that system. So the general experiment would look as follows. One would have the particle trapped within a harmonic potential and cool it down very, very cold so that it's in the quantum ground state. The lines here represent the different eigenenergies of the system. And then when the particle is in the ground states, the probability distribution corresponding to the ground state has a shape which is something like this. It's kind of resembles a Gaussian function. And then if we very quickly change the trapping potential, we then can, if we do it fast enough, we don't distort the probability distribution for the wave function, but we do cause the particle to then be in a superposition of different motional states, if we do this correctly. And then if we wait for some time, the different components of our motional superposition state evolve in different ways. They evolve with different speeds and pick up different phases. So then in the end, when we measure the system, we measure a pattern like this in the probability distribution. So when we try to measure where the particle is in the end, we might see these fringes. And if we see these kind of fringes here, that would indicate that coherence gets preserved between the different components of our superposition state at the end of the experiment. So, so these are the kind of approaches that one could follow if one wants to probe collapse models, these spontaneous collapse models, which are describing why quantum physics is not obeyed in the macroscopic world. Now, if we talk about the second question that I raised at the start, that of unifying quantum physics with general relativity. So right now in physics, we've got this wonderful standard model, which has got all these particles, and it describes the three of the four fundamental forces of nature. And we know that these three fundamental forces are described by quantum physics and quantum field theory. And then the fourth fundamental force, gravity, we don't know if it's described by quantum physics and quantum field theory. And attempts by theorists to come up with a quantum theory of gravity have been somewhat unsatisfactory until now. And as well, experimentalists have not provided any evidence that gravity is quantum yet. So if gravity is quantum, there should be a graviton, for instance. That would be a particle which mediates the gravitational force. And that would be the strongest evidence that we could have that gravity is a quantum theory. But unfortunately, gravitons, they're not detectable. It's completely unfeasible. So instead, to learn whether or not gravity is described by quantum physics, we have to go about looking for indirect evidence. So astronomers are looking at the skies and looking at the cosmic microwave background, and they're looking for signatures from the early universe which might indicate that gravity is a quantum theory from back when the universe was very small and everything was tied together and very hot. But as well as using astronomical observations, we can consider doing experiments in the laboratory to see if we can see any quantum effects of gravity. So the main approach that we could follow in the laboratory is to test whether or not gravity can cause two masses to become entangled with one another. So we know that if we've got two charges, for instance, the electromagnetic interaction between them can cause the two charges to become entangled. And in the same way, if gravity can cause entanglement between two masses, then we would know that gravity is quantum in nature, just like electromagnetism is. So we could consider it this kind of an experiment here. We could have a source mass, which we prepare in a superposition of two different locations, location 1 and location 2. And the source mass exerts a gravitational pull on a test mass over here on the right. And then we wait for some time and we look at how the overall system looks like. So the component of the source mass at position 1 exerts a relatively weak pull on the test mass. And over the time, it will pull the test mass only a small distance over to position 4 here. Whereas the component of the source mass at position 2 pulls on the test mass more strongly, and the test mass gets pulled closer to further along to position 3. So then in the end, if we measure the system, we would see that there's a correlation between the source mass being at position 1 and the test mass being at position 4, and the outcome of the source mass being at position 2 with the test mass at position 3. So this can be written in this fashion down here, and this would be an entangled state. So this would be the outcome that we would expect if gravity can give rise to entanglement between two different masses. Now, so that is the general idea. The more serious proposals might look something like this. We might have two particles, particle A and particle B, each of them going through a matter wave interferometer. So particle A can go along path 1, whereas path 2, and particle B can go along its path 1 and path 2. And so then at this point here, given by the dashed line, we see that the state of the overall system is described here. We've got particle A in path 1, and the superposition of particle A being in path 1 and of particle A being in path 2, with a superposition of particle B being in path 1 and particle B being in path 2. And this overall state, it's a separable state. It's not entangled. And if we expand it out, we see these 4 different components. And then if when the particles move along, by the end of their trajectories at this point here, the overall system might look like this. So if we have path 1 and path 2 being close together, close to one another, there can be quite a strong gravitational pull attracting the particles in path 1 and path 2. And then that would cause the energy, an energy shift of the components, which has particle A being in path 1 and particle B being in path 2, this component here. And this energy shift then means that this component evolves with different dynamics than the other paths. And it can then give rise to a phase in the end on this component. So this phase will depend upon the interaction strength, the gravitational interaction strength, and the time for which the particles interact. Now, if there's this phase arise, then the final state of the system is an entangled state. It's not immediate. It's not obvious at all that this is an entangled state. But if, for instance, phi is equal to pi, this would be a maximally entangled state. It would be a Bell state, just written in a funny basis. So detection of this entanglement caused by a gravitational interaction could be detected in this fashion as well. Alternatively, instead of using particles which are freely flying through space, one could use particles which are trapped. So here we've got particle A in one trapping potential and particle B being in another trapping potential. And if particle A and particle B are each prepared in superposition states, we should also see entanglement being introduced. We might also see that gravity introduces entanglement between particle A and particle B in this case. Okay, so that's the motivation behind this work, that we want to be able to have quantum systems which involve particles with very large masses. And in this way, we could study quantum physics in an entirely new regime. And then in this way, we can learn whether or not spontaneous collapse models are true. And also, we could find whether or not gravity can introduce entanglement between the masses. And if we found that, then it would tell us about the nature of gravity, whether or not it's quantum. So in the next section, I'll tell you about some of the different experimental systems that we could use to study these questions. So first of all, whenever you're setting up a real quantum system in the laboratory, there's competing demands on your quantum system. You would want the quantum system to be controllable, first of all. You would want to be able to initialize the quantum system in a particular state. And in the end, you want to be able to measure it. So controlling the system inevitably involves disturbing it somehow. And at the same time, you want to be able to have your quantum system very well isolated from its surroundings. And you see that there's conflicting demands here. We want to be disturbing it, but at the same time have it isolated. So the reason that we want it isolated is that if there's any coupling of our experiment to the surroundings, then this is going to cause the quantumness of our system to be lost. This is going to cause decoherence in our system. So then if we wanted to use our quantum system for testing whether or not there are these collapse models, whether or not these collapse models are true, then we'd be trying to measure this effect of the collapse. So the spontaneous collapse would cause decoherence in our system. And the decoherence would be the signature that we would be looking for. But we would want to be distinguishing the decoherence that is from nature, that's spontaneous. We want to distinguish that from the decoherence that is just technical in our experiments. So that's why we want to decrease the technical sources of decoherence as far as possible. And that's why we want to isolate our system. And as well, if we wanted to use our quantum system for finding whether or not gravity introduces entanglement, then we would want the coherence in our system to survive long enough that we could measure the entanglement. Because the gravitational interaction between two masses, it's very, very weak. And it would take quite a long time before there would be a measurable amount of entanglement evolves between two masses. So So in this time, if there was any decoherence happening, then that would get rid of our entanglement between the masses, and then we wouldn't be able to measure anything. So we would need our decoherence rate to be less than the rate at which the entanglement gets produced in our system. And this is very challenging to achieve because gravity is so weak. So if we had, I mean, there's many different quantum systems out there, and they all have different requirements, but many of them have the following requirements in common: that for them to achieve isolation from their surroundings, they put the quantum systems are in vacuum, and this means that decoherence caused by background gas collisions is reduced. The systems are made very, very cold so that decoherence, because of black body radiation, is reduced. And as well, electric field shielding and magnetic field shielding are applied so that effects of background electric fields and background magnetic fields are reduced. So then that brings us to what kind of experimental systems we would want to be using to be then exploring quantum physics in a regime with large masses. So I've already mentioned that people are using matter wave interferometry they're doing these experiments already 20 years ago with buckyballs, which weigh around about 700 atomic mass units. And they found that coherence persisted there. But over the last 20 years, the experiments have come a long way. And last year, there was an experiment observing interference with a molecule weighing 25,000 atomic mass units. So this is huge. And so from an atomic perspective, it's very, very large. But it only weighs around about 10 to the minus 20 grams. So most people wouldn't really call this macroscopic at all. So matter wave interferometry experiments are a great approach, but let's see if we can get to larger masses with a different approach. So other approaches that are out there in which people have got tremendous control of their quantum systems, in particular the motional states, include trapped ions, Bose-Einstein condensates, atomic clouds, neutrons. Also, there's experiments with superconducting circuits like squids, which involve many Cooper pairs. But then the approach which has really yielded, which has really been followed to explore quantum physics with large masses so far, has been the field of cavity optomechanics. So in cavity optomechanics, in the general kind of experiment, there would be an optical cavity consisting of two mirrors. And one of the mirrors is mounted onto a very thin membrane. And then the light inside of the cavity will exert a radiation pressure onto the membrane. And because of this radiation pressure, then there's a coupling between the light and the motion of the membrane. So the membrane has got motional modes in much the same way as a drum has motional modes. So it's got many different motional modes, and we can isolate one of them that we want to investigate. And people use light to be able to cool down one of the motional modes of a membrane all the way down to the quantum ground state. And then there's been experiments done where light has been used to prepare the motion of the membranes in non-classical states into quantum states. So there's many different approaches to cavity optomechanics. I mean, there's many different shapes and sizes of experiments. Typically, they're maybe around about 1 nanogram in size, which is already 10 orders of magnitude higher than what's being done with matter wave interferometry. And the different setups can look like this. And in these systems, the real big results are that they've achieved ground state cooling of the motion of the systems, and then this enables quantum states to be investigated. So then they've gone on to observe entanglement between different mechanical oscillators. But then, if we want to really have a system with a very long coherence time, there's a limit in cavity optomechanics. And that is that we've got this membrane, but in the end, it's going to be clamped onto something. It's going to be fixed here. And this connection to the outside world, it's a mechanism for decoherence, because there's then a coupling to the surroundings. So then there's now experiments being followed which use ideas from cavity optomechanics, but instead of having a fixed membrane, they have particles which are levitated so that they're weakly coupled to the outside world. So some people follow optical levitation, others electrical levitation, and some magnetic levitation. Now, optical levitation has yielded very great results. This year, there's been a paper where they've got ground state cooling of an optically levitated nanoparticle of glass. However, there's a fundamental limitation on how long the coherence times in the system can be, because the particles will inevitably absorb the light, which is used for trapping the particle. So the particles get trapped using, in the same way as optical tweezers are used to trap particles. And any absorption of the light is a way that the particle's motion can decohere. In electrical levitation as well, the electric trapping fields cannot be perfectly stable. And if the electric fields which are used for trapping are not stable, then the trapping potential changes in time. And then this causes the motion of the particle to decohere. Whereas magnetic levitation can be conducted in a fashion in which, in principle, the trapping fields can be perfectly stable, and the particle won't have any intrinsic losses or any significant intrinsic losses. So then that brings me to the third part of my talk, where we look into magnetically levitated oscillators, which I hope you agree seems to be a good approach to studying these problems which I raised at the start. So studying quantum physics with large masses, and to also see if entanglement can arise because of gravity. So within magnetic levitation, there's some different things we can do. We could have a diamagnetic particle trapped using strong fields produced by magnets. But actually magnets, the dipole moments of magnets drift in time. And then this will cause the trapping potential to be unstable, and it would cause decoherence of the particle's motion. So there's a limitation here. We could have a ferromagnetic particle trapped above a superconductor, but the ferromagnetic particle, its dipole moment drifts in time, and this will also cause its own motion to decohere. So that the approach that seems to be may be the most promising is to have a diamagnetic particle trapped using external currents, because the magnetic field because if one had currents along a superconducting coil, the currents can be perfectly stable in time. And this means that the magnetic fields produced by the currents can be perfectly stable in time. And that's why a diamagnetic particle doesn't have the same intrinsic losses as a ferromagnetic particle. So the general idea for trapping a diamagnetic particle is as follows. We have the two different coils in an anti-Helmholtz configuration. So then the magnetic field that's produced between the coils is in this quadrupole configuration. And then it's possible to trap a diamagnetic particle in the very center of the quadrupole field. So the diamagnetic particle wants to be where the field is minimum, and that's at the center of the quadrupole field. And the diamagnetic particle, if it's an ideal diamagnet, will expel the magnetic field lines away from its interior. And so this means that the diamagnetic particle distorts the magnetic field to some extent. And if the diamagnetic particle moves, then the field lines are also going to move. So then if we've got a small coil positioned quite close to the trap, then the flux going through this loop is going to change in time, depending on the motion of the particle. So by measuring what magnetic flux is going through this loop using a very sensitive magnetometer, we can then learn about the motion of the particle. So that's the background to the approach that we want to follow, or that we are following. Now, some more details about it. So to have an ideal diamagnet, one needs to use a type 1 superconductor, which expels the field lines by the Meissner effect. And in our system, we use lead microspheres, which are between 1 micrometer and 100 micrometers in size. And they range in mass between 10 to the minus 11 and 10 to the minus 5 grams. So we're now getting closer to truly macroscopic system. And the masses that we have, at least in the theory proposals, seem to be enough that we can really start exploring these effects. Like, is there to be really exploring parameter regimes where the collapse models are really predicting effects to be observable. So then I said that I'm involved in different experiments. So in one of the experiments in Vienna, they use quite a macroscopic system where here we see all the coils which are used for the lower coil for trapping the particle. So sorry, here are all the windings of the lower coil for trapping the particle. And then placed on top of this is another set of windings. And then the whole system is placed inside of some shields, and it's placed inside of a cryostat. So the whole system is very, very cold, and it's in an excellent vacuum. And in the system, then the particles can be levitated, and the motion of the particle can be read in the way that I described, where it gets read by a magnetometer. So whenever the signal on the magnetometer is, whenever we then take a Fourier transform of the signal on the magnetometer, then there are two peaks that we see here. And these peaks correspond to the motional frequencies of the particle, which are at around about 70 hertz. So these are the trapping frequencies of the particle. And so then everything's there so far. So the particles are trapped. The motion can be read out. So then the next step which is currently being pursued, is to ground state cool the system. So it has to be in the ground state before we can prepare interesting quantum states of motion. So to do ground state cooling, we could modulate. We have to apply feedback to the system, and this can be done by applying some additional signal onto the trapping coils, or as well by applying additional magnetic fields to the system using auxiliary coils. Though ground state cooling has been demonstrated in various quantum systems. It's for instance, in trapped ion systems, in which the trapping frequencies are quite high, of around about 1 megahertz. As well, I said that ground state cooling has been recently done in an optically levitated system of an optically levitated nanosphere. But in that system, the trapping frequency was also very high. It was like 300 kilohertz. So it's much easier to cool down particles to the ground state if the trapping frequencies are high. But in the experiment that we have here with magnetic levitation, the trapping frequency is only maybe 100 hertz or so. And it's much more challenging to ground state cool because the system is much more sensitive to background sources of noise, in particular vibrations. So anybody walking past, any train going past outside, buses, cars, whatever, cause slight vibrations, which are enough to really heat up the motion of the particle. So that's why in these systems, it's very important for there to be excellent vibration isolation, for the system to be very well decoupled from the surroundings. And for that, we need to use the same kind of technology which is used in LIGO. So in LIGO, they've got the mirrors, which are very well isolated from their surroundings, so that they can pick up the very weak gravitational wave signals. Then, assuming that we can get all the way down to the ground state, we want to be able to control the system. We want to be able to prepare it in quantum superposition states. And we could do this by, as I showed before, we could change the trapping potential in time. So by suddenly changing the trapping potential stiffness, we could then prepare the system in a superposition state and of different motional states. Alternatively, the particle's motion could be coupled to a superconducting qubit, because already the particle's motion can be read out by a squid. So this is going along the right lines to connecting it to a superconducting qubit. So if we wanted to go down the lines of preparing quantum states of motion by squeezing and displacing the trapping potential, one of the approaches that we might want to follow is to build a kind of skate park for a particle, a magnetic skate park, where the trapping potential at different points has got different stiffnesses, so that the particle can smoothly evolve its state from here to there, so that there's no sudden changes in the system that might cause decoherence. But to make a kind of skate park like this, we would want to have a chip-based setup so that we can have really good control over the magnetic field that the particle experiences. So, as well, another reason why we might want a chip-based setup is then we could have more control over the trapping potential, and we could make a double web potential. And then we might be able to trap two particles close to each other so that we can investigate whether there's a whether gravity can cause entanglement between the particles. So the approach of using a chip-based setup is being followed in Gothenburg, over here where I am. And here we see the general scheme. We've got these two loops which carry current in this anti-Helmholtz configuration. And in this picture, we've got two different chips. Each of them have got currents going in opposite directions, and the particles trapped in between. And then on the right-hand side here, we see the different chips. We see the upper chip here with all the different windings, and a hole in the middle where the particle can sit. And down below here, inside of the hole, we see the lower chip with some of the windings. As well, with the chip-based setup, we can make planar traps. So to achieve an anti-Helmholtz configuration, you don't need a loop on top of another loop. Instead, you can have one loop surrounding another loop, and then there will be a quadruple potential above the plane where a particle can be stably trapped. So here's a current configuration which resembles this. And in Gothenburg, there's been lots of very pretty planar traps being made. However, many of the with the chip-based setups, there's been a lot of problems caused by the particles sticking to the substrate. So the sticking forces depend upon the surface area of the particles, whereas the lifting forces depend upon the volume. So the small particles that we have of a few microns have got very unfavorable surface to volume ratios. So it's very hard to overcome these sticking forces. But this is just a technical problem that we'll have to overcome. As well, involved with magnetic levitation, we've got other challenges. We've got, it's possible to have trapped magnetic flux inside of the particles. And this means that they don't behave as a perfect type 1 superconductor. They behave as a type 2 superconductor, and then they're not an ideal diamagnet anymore. As well, as I said, we need very good vibration isolation in these systems because the trapping frequencies are so low, and efficient readout is also a challenge. So in conclusion, there's these, I hope I've convinced you that following the approach of having magnetically levitated microparticles is is promising, or a potential way to study quantum physics using large masses in large superposition states. And in these kind of systems, then we hope to get into a regime where we can test collapse models and also test whether or not gravity can mediate entanglement, and this would indicate whether or not gravity is quantum. And another thing that one can do with these systems is make very excellent sensors. So the people that are in these different experiments, so the group leader here in Gothenburg is Wieczorek, and I work together with Martin and Cinzia. In Vienna, there's two different experiments. There's one with a macroscopic setup led by Markus Aspumeyer, and working on that is Joachim and Philip. And then as well in Vienna, there's a chip-based setup led by Michael Trupke, with Stefan and Dominic working there. So, muito obrigado pela sua atenção e vocês têm perguntas para mim?
Thank you very much, Gerard, for the very nice talk. So, questions?
So, hi, Gerard. Great
Hi, Andre.
to see you again, man.
Nice to see you.
So, very, very beautiful talk. So, my question is more like, I think for an experimentalist, it should be a very stupid question, but I don't understand. So, when you're describing the way that you create your quadrupole trap,
yeah.
So you use normal coils, right, to create the trap. So you're saying you're gonna know, okay, you use your squid. There's very sensitive to notice any movement of your particle.
Yeah,
that's great. But when you have your coils, they're wires, right? And they'll, although you're in a cryogenic chamber, they're gonna heat up because of the current. So there'll be a noise in the magnetic field that you're creating.
Yeah.
So are you able to stabilize the magnetic field so that the squid is capturing really the changes that you get because of the motion of the particle and not because of the vibration? I don't know what's going to happen to those wires, but wouldn't it be better to use? Yeah, go ahead. Yeah, though I think you're.
So the coils are made of superconducting material. So then.
Oh, okay. Oh, okay. Now it's clear. I thought it was because you showed the picture of the wires. I thought they were just regular coils, and that didn't make sense to me.
Yeah, I think those wires are made of niobium. So at low temperatures, they're superconducting. So then they're non-resistive, so they don't heat up. So then we don't have that source of noise, at least.
Oh, okay. Now it's clear. Okay, man. Thanks.
Yeah, I'm curious. So you mentioned at the beginning you have your two masses of 1 microkilogram. You will approximate another mass. I'm curious how close should be the other mass to be much stronger than gravity, for example, than gravity from Earth?
Fine. Yeah. So this is something that I think cannot be achieved. So gravity from Earth will always be stronger, and this is a problem. So things fall really fast. Like if we need 5 seconds for between two very, very, very close together masses, if we need 5 seconds for entanglement, any sizable entanglement to evolve, in these 5 seconds, they fall by a ridiculous distance. And unless we try confining the particles vertically, but it's quite difficult to make sure that the confining force is only pointing upwards and not slightly to the side. One can think about performing the experiments in drop towers or performing the experiments in space. I think space is a better approach than drop towers, but you don't want to put an experiment in space either. So it's challenging so definitely for any system, or at least this kind of a system, would be able to investigate the collapse models before it would be able to investigate the effects of gravity. So the collapse, or to start to get interesting results about collapse models, is an easier task.
Okay, so gravity is from Earth is like a big bath, big reservoir.
Well, yeah. I mean, I don't know if I'd call it a bath. If that suggests something noisy, I think it's a constant potential.
Yeah, but okay, but it has a non-trivial effect.
Yeah,
on your mass.
It causes experimental complications. Yeah, big complication.
But regarding this question, isn't like the shape of the chamber, the sort of pointy shape that is closer to the particle, for instance, that will be even stronger than any variation of the gravity field of Earth, right? So shouldn't this be even more complicated than compensating to Earth's gravity? I mean, the gravity by the massive chamber that you have, for instance.
Yeah. So I guess it's a question of distances, like, so the particles in some of the proposals are really separated by a distance of a micron or less. If the particles are a micron in size, then they're separated by maybe a tenth of a micron or something. And that's maybe not so ridiculous to think about. If the extent of the motional wave functions, it's orders of magnitude lower, because really they're heavy. So then they don't have very large motional wave functions if they're in the ground state. But I think Earth's gravity is heavier than the chamber, and then there's a question mark over what's a stronger effect, the chamber or the neighboring particle. I don't know.
More questions?
I guess if you make the chamber fairly symmetric, then it's going to cancel out.
I have a question. Did you mention the theory by Diossi and Penrose about the spontaneous collapse? And I know that there are plenty of theories, as for example, Gerard, Rimini, Weber, Pure. And my question is, how to discern about these theories, or your experiment is not about how theory could describe well the spontaneous wave function collapse. Just about to test if gravity is playing a role in this decoherence.
So let's say, so yeah, the experiment would be able to test the different theories, the different collapse models. In principle, it wouldn't be limited to anything related to gravity. I just mentioned the Diossi-Penrose model because it is it's kind of connected to the second proposal. But then were you also asking how would you distinguish between the different models or not? Or have I answered your question?
Yes. My question also is how to discern about these theories, because in Gerard Higgins Weber theory, they also have the effect that if you increase the number of particles, and of course you are increasing the gravity, you also has the effect of spontaneous collapse. How to discern about this? For example, these two theories.
I guess maybe some of the theories depend in different ways. I mean, if we double the size of the system, if we double the size of the wave function, if we double the mass, maybe the different theories are going to predict different outcomes. Maybe some of the theories predict a different increase in the decoherence rate, but I really don't know. I don't definitely far from an expert on any of this.
Okay. Thank you. Another question, just by curiosity. I was thinking about Popper crucial experiment notion. So, do you think that an experiment testing if gravity plays a role in the coherence? Do you think that is possible to say that is a crucial experiment in the sense that it's possible to say yes, no in a clear cut manner?
Yes, like what would it reveal about the nature of gravity? Or what would it reveal about the nature of
Yes,
quantum physics?
because there are so many sources of the coherency from
Yeah,
the
yeah, for sure.
outside.
Yeah, that's something that's quite, I mean, so for this system, there's the two motivations, and one of them is easier to achieve. I mean, it's easier to get to a regime where we can test the collapse models, but the experimental signature, it's not nice distinguishing one type of decoherence from a potentially natural source of decoherence, a spontaneous decoherence, from a technical source of decoherence. That's quite a difficult thing in principle to do and to really prove, but I think it should be doable. And whereas the other motivation, I think it's a nicer signature, but it's not as easy to get there.
Okay, thank you again.